plenary presentation, but before I would like to say a few words about our keynote speaker for this presentation. The title of the presentation is BIM-based design of megatall projects, Lakhta Center case. And the speaker for this presentation is the leading architect of Russia, Philipp Nikandrov. Philipp Nikandrov has participated in many projects of high-rise buildings. Some of these projects have won the awards, different awards, and this specific project that he's going to talk about is the well-known tower that was built in St. Petersburg. The history of its construction is design and construction is quite long. Finally, it resulted as the headquarters of the Russian company Gazprom, and Philipp Nikandrov was the chief architect and head designer of this project. And it is very, very interesting to hear the story from the first person that was participating in this project. With his expertise of 25 years of work in the area, international projects, and so on, we are sure that this presentation will be breathtaking. So, Philipp, please, the floor is yours.
Hello. Hello, good morning. Can you hear me? Hello?
Yes, we can hear you.
Okay, you can see and hear me. Okay, good morning. Good morning, everybody. Let me switch to the screen. Can you see my screen now?
Yes, Philipp, everything is fine.
Okay, great. Okay, thank you for confirmation. Let me introduce myself. My name is Philipp Nikandrov, but also thank you for introduction to the chairman. I represent a company, Gorproject. This is a group of companies. We are one of the leading Russian design companies. Over 300 designers, architects mainly, and structural engineers, MEP engineers. But also we have daughter companies, United Facade Company, dealing with facade design, complex facade design. And also we have one of our daughter companies, BIM Academy, which was established quite a long time ago. We're a relatively young company. We're on the market over 15 years, but we were one of the first companies in Russia introducing BIM technology in design process. And our BIM Academy was involved in many educational projects. So mainly it's educational, but also it helps us a lot to design and teach our colleagues in-house. But also we invested a lot in popularization of tall buildings and high-rise buildings. And we published, until last year, we published a regular issue of high-rise tall buildings magazine. This is one of the glossy bilingual magazine. And also Green Buildings is another magazine that we published. And of course, it was a lot of articles about BIM design. You can see on the cover one of our buildings and BIM model on that. And of course, we love high-rise buildings. Mainly we design unique projects, not necessarily skyscrapers, but a lot of skyscrapers, and a few of Moscow City skyscrapers we worked on. You probably know Eurasia Tower and IQ Water, Evolution Tower, Federation, and Lakhta Center in St. Petersburg. This is the artist's impression of iconic high-rise architecture. You can see, you can recognize buildings from all over the world, New York, Paris, London, and Frankfurt, and Seoul, and Hong Kong, and many cities, Dubai. But of course, each of these towers is iconic, and these nations are proud of them. Icon, of course, it's a symbol. So when we call skyscraper iconic, of course, it's a symbol as a 7 wonders of ancient world, or 7 new wonders of the modern world, and of course, many wonders in many countries. And now it's about size, about height raise, and skyscrapers are definitely the flagships of construction industry, and many nations are proud of their icons, and of course publish them on banknotes and postcards and postmarks, stamps, and of course it's sometimes it's a target, and we just recently celebrated. Of course, it's a great tragedy. We remember this 20 years ago, September 11th attack. Of course, skyscrapers were the target, as similar to Temple of Artemis at Ephesus, and because it's so powerful, skyscrapers are so strong and powerful symbols of ideology and economics and nation, the power or empire. But also, skyscrapers is just a typology of buildings, and most of skyscrapers and high-rise buildings are just built not for the symbol, just for money to get profit. But some of them on this sort of skyline of skyscrapers, some of them are higher, and some of them are more significant, and they are landmarks, and they have to be vertical dominance amongst other vertical dominance. So basically, when you have the height raise all over the city, like Hong Kong, Shanghai, Dubai, then some of the towers are more significant, and they have to be treated as symbols. This is the skyline of Shanghai, and now you don't recognize any difference, but we have few towers that are really symbols of Shanghai, and they are what we call megatall or supertall skyscrapers, over 300 meters, but sometimes over 500 meters. But in 21st century, in 1931, Empire State Tower in New York, it was above 400 meters. So one of the first towers above 400 meters as a landmark. And it was also, it was a record of construction. So it was built, the whole tower was built for record-breaking 14 months in 1931. And nobody actually could make it any faster. But if we look at the World Trade Center towers or Empire State Towers, Empire State Building, the reason why they were built so quickly is in the high level of repetition. So basically, it's extruded block, and you have very repetitive design. You have possibly 50 floors without any change. But yeah, of course, the columns gets slimmer, but and maybe you lose some lifts, you get some lifts, but basically the design is repetitive, and this is a reason why these buildings were designed and built so quickly. But you can see the modern skyscrapers. You also have a certain repetition, like in this pagoda in Taipei. You have certain block of over 10 stories, which gets repeated gradually, but again, you have various difficult shape, but again, you have many repetition. In this building, for instance, in Kuala Lumpur, Petronas Tower, of course, it's a symbol of Islamic architecture, contemporary Islamic architecture based on Islamic pattern in the plan. So it's very, very ornate plan, but it's repetitive. Again, it has many repetitions, and the beams are similar, the columns are similar flow height, slab to slab. So it helps to prefabricate and design quickly and build quickly. But also you have in the beginning of 21st century, you have buildings with more difficult shape, with more difficult shape to design and build, more complex, which has much less repetitions. And some of them are mega skyscrapers like these two, Burj Khalifa and Kingdom Tower. But in Burj Khalifa, you also have tiers, and with repetitive design, you have one above another, but it helps, again, repetitions help to design and build. And the tallest 20 towers in the world, what we call megatall, is above 600 meters, and you cannot find, mostly built in Asia, in China and Dubai, Middle East, but none of this is in Europe. European towers are smaller. So if you look at the European towers, most of them actually in Russia, in Moscow or St. Petersburg, but also London, the Shard and Frankfurt. And they are not so high compared to Asian skyscrapers, but they are more interesting architecturally, they are more sophisticated and more innovative. Like this one is not very high in London, but it's very innovative and in terms of sustainability. It's really ecological. Or this in Barcelona. And we have in Russia, we have our tradition of high rise, and we entered height race in 20th century with Soviet's Palace, which was supposed to be 400 meters tall. And it was started in construction in 1931, at the same time as Empire State Building was finished. But it was only lower levels and basement constructed when the first, maybe first floor and the Second World War started. It was the construction was terminated, and then structure was dismantled for fortification uses. The second landmark actually successfully finished was University Tower, which until 21st century was the highest tower in Europe, 240 meters. And Ostankino TV Tower, 540 meters. For 2 years, it was the highest structure in the world, built in 1967, which is 54 years ago. And it was designed by Nikitin and Vladimir Travosh. Vladimir Travosh is our chief structural engineer in Gorproject. So we're all proud to work with him on skyscrapers, on many skyscrapers. And he's a leading expert in structural engineers of skyscrapers in Russia and internationally. Those towers of 50s in Russia, they were very ornate, but you can see the level of repetitions. Again, very repetitive, which was simple to design, again, like university. But in 21st century, you can see the new generation of towers that we call twisters. And one of them is the Evolution Tower that we designed, and it was finished in construction in 2015. It's quite remarkable. It was it's really recognized as an icon of Moscow. It has a twist of over 150 degrees, and it twists. Each floor twists 3 degrees floor to floor. So 3 degrees, 3 degrees, 3 degrees, and overall the body twist 159 degrees. But again, this is a repetition. So and we didn't design in BIM. That one we designed in from 2011 to 2014, and basically on AutoCAD, not on BIM. So we started introducing BIM at the time when we designed that. But because of the again the high level of repetitions, we can manage it in time. It's quite unique in architecture, but also in facade engineering. And some of the elements we used in Lakhta Center. At the time it was finished, the facade, it was the world's largest cold bend facade. You can see this is you can see the bend. It's actually a curved facade, curved glass, slightly curved, and it has a very unique optical effect. It rotates reflection of in this curtain wall, rotates the reflection of Moscow panorama skyline by 90 degrees. So you can see it's vertically. There's a skyline vertically, and the reflection of skyscrapers, Moscow city, horizontally. So when you see this clouds floating over these towers up and down by blown by wind, but not horizontally, it's quite a rare effect. Yeah, it's quite bold twist, and as I said, the new generation of skyscrapers called twisters that we can design now because of BIM, because of building information modeling. We have these softwares to design it quickly and build it quickly. And before, without BIM, it would take many years, maybe 10 years to design, and a very long time to build. So this is a new generation. Not because we can build it, we have this whole, complex geometry like Lakhta Center, which I will be talking about in a minute. Again, Evolution Tower was quite simple. So it's very complex shape, but it's a simple idea. It's a straight vertical core and 8 columns surrounding the core and 4 corner columns. It was difficult to build corner columns with a special shuttering design for this, but as you can see, it's a repetition. So the same floor plate rotates 3 degrees, and it's simple. But again, you have to, each floor you have to design separately. You have to the design reinforcement of each floor separately from other floors. So there is a repetition, but it's not that straightforward. In Lakhta Center Tower in St. Petersburg, it's more complex shape. So if you look, this is a scale model I have in my hands. It's extrusion vertically, but twisting, and tapering and bowing. So it bows and it gets into the pinnacle, into the point. So all the mass gets concentrated in one point, as similar to historical domes and spires. That's some images of completed project. It was finished in a couple of years ago, but it's still under construction because of there's a large scale. Phase 2 is under construction. The embankment, surroundings and landscape and fit out works. So it's not yet opened for operation. And the project took, of course, a long time. This is a night image with architectural lighting, and some of the aerial images that you can see. Overall area is about 400,000 square meters, and gross lettable area about 150,000 square meters. The height, overall height, 462 meters, which makes it the highest tower in Europe. You have the main purpose is offices of Gazprom, headquarters of Gazprom, moving from Moscow. But there are many other functions in the complex, which includes science museum, educational center with planetarium, quite unique, 500-seater transformable multipurpose hall, and various supporting functions like fitness, retail, restaurants, and of course underground car parking for 1,800 car spaces. This is our image of rendering, visualization, and actual photos of the construction site with phase 1 almost completed and phase 2 under construction here on the Gulf of Finland, in the outskirts of St. Petersburg. So quite pleasant space and interesting to get there. So I would recommend you to come and see when it gets finished. This is construction process, and I will talk through the difficulties and challenges we had in the process of design. The night view. One of things we are proud of and quite remarkable. The tower received was certified as LEED Platinum by LEED, which is one of the major ecological green organizations responsible for certification of green buildings. And the tower received platinum, which is the highest degree, and the base buildings, podium buildings around it received gold, called Lakhta Center multifunctional building, which is below. But if you look at the criteria of the design to be certified, you have important things like sustainable site and water efficiency, energy, atmosphere, materials, resources, and quality of air, for instance. But what's important is innovation. So if you look at innovation, is 6 of 6. So you have a highest point. You have 6 points for innovation, and for both cases, we have 6 of 6 in innovation. So which is why we received one of the reasons we received platinum. There are lots of innovation, but just mention few. The big data in building management is a multi-level monitoring of all parameters of the buildings and the state-of-the-art engineering. We have double skin ventilated facade with natural ventilation, and energy efficient elevators which recuperate and recover the energy during braking process. Also, we have ice generators saving energy, and very smart contemporary waste disposal system, which is vacuum transportation and recycling of waste. And we have quite a lot of innovation in facade and in using ATFE roof, which is synthetic materials, not glass. Of course, facade management system, BMU, building management systems, which we had to invent basically because they were not in the market to service this very complex shape of the tower. It's a view from the top. But the history of the project is quite interesting. Started in 2006, Gazprom established international competition, architectural competition, inviting 6 teams, famous architectural studios like Daniel Libeskind, Jean Nouvel from France, OMA from Netherlands, Herzog de Meuron, Switzerland, and Fuchs Associati from Italy, and RMJM London from UK. And I worked on, I was director at RMJM at that time, and was a chief architect in this competition entry and later. But the site for this project was different. So it was closer to the center, 5 kilometers from the city center, on Orta. Later project has been replaced. So if you look at the St. Petersburg, this is a St. Petersburg map or scheme diagram showing the boundaries. St. Petersburg includes actually 9 cities and 21 villages, and the central St. Petersburg, which is marked up as red, historical is as presented here is preservation area protected by UNESCO, is a UNESCO World Heritage. And the first site, the actual site is here when where Lakhta Center was built, but the original site was in there, so it was slightly closer to the central center of St. Petersburg. And center of St. Petersburg is really huge. So if you compare in the historical center of St. Petersburg, which is marked up red here, to the Venice. So this is the Venice. It's a real site. Venice is much smaller, the entire Venice, than the preserved St. Petersburg area. The first site was located in here, but due to the it's actually was at the place of ancient Swedish fortress, and the later fortress of 16th and 17th century called Nienskans, which was demolished by Peter the Great. So some of the archaeological remains there, and this was one of the reasons of objections to build in here in this peninsula. And due to because of the remains of this fort, but actually the shape of the fort was inspiration for the design. So you can, if you look at the this is a pentagon in the tower basement, right, which gets developed in the 5-shaped star, which was inspired by the actual fort. And this is the plan of the tower. If you look at from the very top, you can see that exactly that that shape, which looks like a flower, Baroque flower. That's a plan. And this is the axonometric of the plan with a central core, circular round core, and 5 square wings that rotate almost 1 degree each floor and taper and twist. In general, the silhouette of the project is a flame. The flame is a logo and symbol of Gazprom, of course, the blue flame. And but we have a flame. Excuse me. That's we can see images of the 2007. The shape of the tower, the idea of the flame, it remained, but we had to redesign a lot, so it became higher. And on Orta site, it was 396 meters tall. On Lakhta, when it moved to Lakhta, that the height increased to 462 meters. But of course, the height is symbolic. And in St. Petersburg, we have many vertical dominants, and most of them are not very pleasant, like these chimney pipes. Like this is a big industrial city, and we have port cranes, but also have TV tower, which is over 300 meters tall, and in the center we have domes and spires. So St. Petersburg is different skyline, and it was important to have the major symbol to be the tower rather than TV tower or chimney pipe. So the project actually relocated 9 kilometers to the west due to UNESCO demands, and as now. So the major concern was this proximity to the Smolny monastery over here. So the tower moved to far away. And it is now at Lakhta district in the northwest of St. Petersburg. And it forms a new marine facade. You can see the football stadium here and a new bridge, suspended bridge. And this is a new district, which is, and the Lakhta Center is a generator that will generate developments in this new part of the city. Of course, the port as well. So there's a new marine facade, includes the new passenger port for liners arriving to St. Petersburg. And the first thing that meets you in St. Petersburg would be Lakhta Center Tower, which is a flagship and a lighthouse on the Gulf of Finland. So after relocation of the project, construction took about 6 years to complete the envelope and the structure and services by 2018, with some breaks, changing the main contractor in 2014 and 2015. So originally Arabtech and then Renaissance as a main contractor, Turkish company, and Arabtech built foundations with Bauer Construction from Germany in 2012 and 2013 finished basement foundation of the tower. The location of the project is, it actually works in the antiphase of the traffic flow. So it actually helps to reduce the traffic flows in rush hours, in peak hours in the morning and evening time. Because the location, this is a over 2,000 car spaces, but not in the city center. It's actually outside. So the cars from city center in the morning would go to the outskirts, which is in opposite direction. So it actually helps a lot to reduce the traffic problems in St. Petersburg. But potentially it's in a plan to arrange a transportation hub, including metro station and railway station, and also using the water transport, the operator type of water taxi, and of course various modes of public transportation that includes buses and metro in the area. And we also designed this pedestrian bridge, but still the dream to connect the park and the new construction site together, and use this water transport for the future. So we talk about construction and the design, but the public uses. This is deeply integrated. The project is integrated into the idea of a city on the water and river, embankment, the amphitheater and stage open to the water, to the Gulf of Finland, and you can watch regatta, windsurfing, and yachting, and various entertainment and performances on that stage. So it's an important part of the life of the district. And of 8 hectares of the first phase, most of the area is about 6 hectares is open public piazzas. So 3 public piazzas, landscaping, water features, greenery. This is a video, but I don't know if you can see it in a good quality. It could be compromised because we're online. So fly around by copter. The shape of the tower, we don't have any repetitive floors. Earlier I explained that the tower gets extruded with twisting, tapering, and bowing. So we have no repetitive floors. So each floor, if you look, we have rotation, twisting of each of the 5 wings. And so it gets smaller, and also changes in the core. And various uses as well. So we have various uses. We have plant levels. We have at the top, we have a rotating restaurant. We have observation deck on the top, and we have offices and meeting rooms and various functions. So no repetitions whatsoever. And if you take the entire project, there is no repetitive level. And the total number of floors is 89. And number of levels is over 100, 101. Basically, it's the most complex projects in the world. Really, it's the most complex skyscraper and maybe project in the world, because this number of floors and non-repetitive. It means that each beam is different. So you have on this floor you have, for instance, 30 beams, but these 30 beams will never repeat again. So next level again, the columns are different, because columns are not straight vertical. They are inclined negatively or positively, and you have to design for this for these columns differently. The plates for fixing to the next column and changing angle, and very precise. It's a steel, mostly steel work and composite structure. The core is concrete, so mainly the structure is a concrete core, and steel beams, composite columns, and metal decking of floor slabs. And this was modeled, again, lots of simulation. To design this very complex structure, you have to do a lot of simulation, a lot of computer simulation. For instance, wind is a major problem for high-rise, and major enemy of high-rise buildings. And you have to design for stiffness, for sway, and we have this central core, composite core, reinforced concrete that takes all the load, and 15 columns that get into 10 columns on the top, and 4 levels of outriggers. It's outrigger levels that are steel frames. This is outrigger. Outrigger is the element that connects external columns to the core by means of this fins. The fins actually trusses. This is steel trusses. So if you imagine, again, referring to the September 11th attack that 20 years ago, this building having 15 columns at the bottom, if you explode all 15 columns, of course, we had to take into consideration new requirements post September 11th attacks, progressive collapse in structural design. But this tower is definitely one of the safest in the world, because if you explode all 15 columns at the bottom, the building will not collapse, it will stay as is. Because these columns will hung by the outriggers. So the outriggers actually support, 4 levels of outriggers support these columns. And even if you explode 1, 2, or all 15 columns, the whole load or vertical load will be transferred to the central core and to the foundations. And the central core has 4 hours fire protection, so 4 hours of fire, which is more than enough to evacuate, to actually escape from the building, from the highest floor. You don't need that long. 4 hours is quite long to sustain. So that's a construction process. You have the central core that is in concrete, so it gets extruded by this special shuttering by Perry, and the steel work surrounding it. And of course, columns are composite, which was unique for Russia. We had to develop special conditions, technical conditions, but as well as the new regulations in Russia for the composite columns. They're actually cross-shaped, and then concreted, surrounded with studs actually welded into the body of the column. And this is, you can see the studs. These are steel like bolts welded into beam. So that what is called composite structure with metal decking and fire protection below. This is fire protection. So 2 hours for the beams and 4 hours for columns. Again, this is about 2 times of NFPA requirements. NFPA requirements, which is American fire regulations, is 2 hours for fire protection, and we have 4 hours here. So basically, it's not excessive. It's actually safe. It provides greater safety for the structure. The foundations are also unique for Russia, very deep, 85 meters long, 85 meters deep piles, 264 piles, circular shaped, 2 meters in diameter, bored into the, because of very weak from soil in St. Petersburg, actually founded on swamp in delta of Neva River. The piles had to go as deep to actually reach the stronger level of clay, of ancient clay, to get supported from below. So it's so-called hanging piles. Total number of 264, and the foundation shaped as a pentagon, which is that shape. And this pentagon is spread at the large area, and by means of the central core and fins, concrete fins. This is a shape of foundation, and this is a pile. This is a pile diameter. You can see 2 meters pile in the metal tube. The Lakhta Center foundation pouring was actually registered as a new Guinness Book World Record. It was the largest continuous concrete pour. It's about 20,000 cubic meters uninterruptedly, 49 hours concrete being delivered to the site from 13 different production plants in St. Petersburg, breaking the world record and making new world record for the Guinness Book as the largest one pour foundation in the world in here. The facilities include the tower and the base buildings here. You have the entrance arch and also the 2 blocks connected with atrium with 250 meters long. Some of the images, but you can see here our representation of media screen, but actually this is a media screen being tested. Is actually also completed, a very large media screen at the entrance, and again atrium and spaces. And here under construction, this has been fitted out. This is a planetarium ball, curved glass, and lots of nice and sexy architectural elements here. And you can see on images and some photos of construction as well. So it's very complex geometry. It's not orthogonal. Everything is curved, really. It's a curved glass canopies, curved glass steps at the entrance, and the supporting elements. For instance, this curtain wall gets supported by glass, not by normally it's aluminum or steel studs or mullions, but here it's a glass. It's one of the highest in the world, 17 meters. One piece of glass, 17 meters, 17, one of the highest in the world. The glass elements fixed to the steel, and they actually hung from the steel. So it's a very unique double skin facade, energy efficient double skin facade, but also this is glass fins supporting up to 16 meters. and a lot of steel arches and steel frame of the base buildings here. As everything is in steel, composite structure with reinforced concrete core and steel with large cantilevers up to 36 meters, 40 meters, and arch span about 99 meters span with bridges. See the bolted connections. And for the facade envelope, we had to manufacture the mock-ups, and also the roof of base buildings is actually quite unique. It had to be it had to provide the shadow for the as a requirement of for LEED certification for the green buildings. But as well as the skylight is not in glass, it's in a TFE, which is a film, cushion, inflated, and it helps to reduce energy for otherwise glass heating if it's glass, right? So it replaced glass to reduce the energy consumption, and the cover of the roof is also for LEED standard. We had to, as a requirement of LEED, heat island effect, we had to have this roof providing the shadow as a mesh, aluminum mesh. The facade, we started from triangulated panels. This is a real scale model like mock-up. And finally, we from triangular facade, we ended up with a cold band like here with large panels, helping to reduce energy consumption. So actually, from this facade in Lakhta Center, very large panels and cold band as an evolution tower. The same technology, we use the same facade contractor from Germany, Gartner. This is evolution of facades. So small triangular panels, smaller, larger panels, and really huge panels of about 11 meters square, each panel of glass, with a double skin facade, naturally ventilated through the corners, and special detectors operate the vents to open in overheating and to close in colder temperature to close this facade. So this is buffer zone gets naturally ventilated in overheating and completely sealed for the greenhouse effect, reducing the energy demand for winter, for colder months of through winter. This is a view of buffer zone, and the facade installation, as I said, 11 meters square each panel, and it's actually bent, cold bent slightly so the whole facade is curved about 90 degrees through the height of 400 meters. Again, this was modeled in mock-up. Not everything you can model by computer, right? You have to see the actual quality of glass and the reflections in reality. So we had to build these mock-ups, and this is a cold bend, as you can see the effects of a cold bend glass. It's very, very smooth transition of light and reflections of sky, and really big panels here. But also unique invention of the engineering corners with lighting integrated into the architectural lighting and BMU, which is build facade management and maintenance system. Architectural lighting is also unique. It's designed for this is a special element. So the color light doesn't go into the offices. It's only the frame of the facade gets lit, not really without any intrusion into the office space and comfort of office. There's some of the videos of Of course, a lot of this had to be modeled in 3D before it gets to the order and on the construction side. The facade maintenance, because of this complex shape, it cannot be serviced by a simple crane. So we had to design special system that that actually moves parallel to the facade without any damage to break the facade or to damage the facade. So the system maintenance unit consists of these platforms on rails. So the rails are integrated into the facade. They are sort of hidden. You cannot see them, but the system actually reaches these rails through the rubber seals. And you have these 2 tiers of maintenance unit that goes up and down, and it's telescopic, so it gets extended or reduced, fixed to this corner rail. With special self-leveling system, it always gets vertical. So none of the towers in the world would have this thing. So it was, again, as I said, it was invented. Some of the drawings, how it works. But the spire is also unique because you have the top of this top 100 meters architectural top, which is decorative, of course, but because it's hidden sometimes in the clouds in winter, the risk of condensation, the risk of ice formation was very high, so we had to model it. This is in construction. You can see this is all the structures in winter covered by a thick layer of ice, and the icicles is a real danger for the tower. So we had to deal with the heating of the facade, which gets operated and detected by special detectors used in aviation for the ice formation on the wings of the airplane. So the same technology was used for the spire. And we had these gutters, the special devices that if you have any icicle and it gets dropped down, and it can be catched by this icicle catchers on the facade. And again, not everything can be simulated in computer. We had to go through the wind tunnel testing and ice testing. This is a test in Canada, in laboratory in Canada, of the ice formation on the roof and the ice formation on the architectural mesh here, and also the pedestrian comfort. You see all these little pipes here. They're actually with meters, and this is to actually measure the wind loads and wind comfort at various public areas around the tower. But most of the, and this is this very top, we have, this is very top of the tower, which is a pinnacle, but it gets a complex of measuring devices for meteorological measurements. And it's important part of the, also aviation lights, it's important part for building monitoring. That's the top of the tower. And this is a structural monitoring software, and part of it is actually current weather parameters. So at the very top, you can measure the wind, the wind speed, the pressure, the temperature, and various other parameters that are important part of the monitoring. And of course, we designed it through BIM. It was in Revit, Autodesk Revit, level of details up to 400. And we created over 6,000 new families of objects in the federated design model with centralized control management. And as a multidisciplinary company, we had to coordinate all design disciplines, architecture, structure, and MEP in this federated BIM model. Just to show you, to illustrate structure, MEP, engineering systems, and this is for the tower. The very complex, all engineering systems in one, so that's as it goes from the bottom to the top. And of course, the major element is a collision check. as a part of the process and the protocol to avoid those collisions. So the collisions may occur only in design process, not at the actual constructions. So due to BIM, we managed to have a very, very smooth construction process as resolving all collisions in virtual reality rather than on site. That's a BIM model, structure and scheme, and MEP, so all combined. But not everything was smooth with Revit Autodesk. Of course, the facade contractors prefer to use CATIA, Dassault, which is now software came from aviation industry from France, for the building fabric with a double curved envelope. And we struggled to build in Revit, but actually managed to combine Revit and Grasshopper to help and through the scripts to actually manage the issues with facade envelope and optimization of panels. This is a process we used. So actually in Grasshopper and then importing to Revit 3D model. But again, as I said, it was difficult to resolve this envelope in Revit itself. That's a process of optimization. You have many different panels, but the task was to optimize and to increase the number of repetitions. The number of repetitive panels, we have over 75%, and then 25% non-standard. But again, to find the solution, you have to go through to change the parameters of the unit, which is a double glaze unit, glass unit, before you import it to Revit. This is a script, and the same we had for the envelope, for the corners, framing shape, and the top of the tower. And this is the actual erection of the installation of facade. The steelwork red, and the concrete is gray here. And this is structural models. Again, structural engineers use their softwares for the design and simulations. But finally, assembling the whole thing for collision check in Revit. And again, the coordination in Revit was an important part. And this is some of the images of course, vertical transportation. So you have to simulate vertical transportation, traffic analysis in a different software called Elevate. The fire prevention system, we have, again, this different simulation of fire, and we had to use a very innovative system of fire suppression called water mist, which is not actually water, it's not sprinkle system, it's a spray of water, which doesn't damage the computers, doesn't damage the furniture and the finishes in the room. Because normally the sprinkle system brings more damage than the fire itself, the water in fire extinguishing process. And here we have this very innovative, it's similar to gas suppression system, but instead of gas, it's a vapor of water. Finally, Lakhta Center was awarded, received many prestigious awards in last year in 2020. We received Skyscraper of the Year from Emporis. It was in Hanover, in Hamburg in November 2020. Emporis Skyscraper Award as a skyscraper of last year. In this year, we received 4 awards from, went to Lakhta Center for as a best tall building 400 meters and above, and best high-rise building in Europe, and best in facade engineering in the world. So it's a ceremony in Chicago. It was recognized as one of the best skyscrapers in the world. But also we worked at the moment in BIM in technology. We work on the ongoing construction of Akhmat Tower in Grozny. This is 435 meters. It's not as high as Lakhta Center, but almost there. It's under construction. You can see foundation design. The architecture designed by Adrian Smith, Gordon Gill, and Gorproject is a lead designer, general designer in that. We're working on the construction of Technopark and Sberbank. Again, very complex building. It's the last project by Zaha Hadid before she died 2 years ago. That's in Moscow, near Moscow. And we work again on construction and design of 15,000 seats ice arena in Yekaterinburg. Again, it's a architectural design by HPP from Germany, but we did with all schematic design and working documentation through the construction drawings, and it's all in BIM, of course, and it's Autodesk Revit, but as well as other software used, Dynama, Grasshopper, Star CCM, and Plus, and other softwares. So some of the images to show you the foundation design, structure, 3D modeling, calculations. And also even the traffic analysis for the crowds, for evacuation and escape. You have to model how people enter. And for this, the designers use PTV Visim, the software to helping in traffic analysis for the entry and egress in the fire escape, especially fire escape, for instance. This is a simulation of egress as people leave in normal mode or emergency mode from the building. And of course, interior and acoustics and the lighting, so it had to be modeled, and the comfort of MEP, the airflows of heating and air changes in ventilation and the smoke exhaust. CFD simulations called CFD, computer fluid dynamics, for the temperature, temperature comfort, and air changes, as well as smoke extract. Sound amplification, acoustics. Again, it's important part of simulation, which with software used by acoustic engineers for the sound. And overall working design documentation, construction drawings with Revit, coordination, collisions check, and coordination of every element here, clashes between structure, pipework, and ductwork, cabling had to be checked in BIM model rather than on construction site. And this is actual construction ongoing in Yekaterinburg of this arena. Again, we used a lot of parametric architectural design, mainly Rhino and Grasshopper. For instance, daylighting in master planning, we use it for daylighting. For instance, we have for the city planning for arrangement of, for instance, residential blocks within the district with providing adequate daylighting comfort for each building and for each facade and for each flat, actually, for each apartment. And even for the landscaping works, for instance, in this our another project, concert hall in Moscow City near our Evolution Tower, we have the big piazza, which is over 3 hectares area, and we have the paving here. It's not non-orthogonal, and it's curved, non radius. It's a elliptical curve. So every actually panel, every slab here has different dimension, and we have to optimize it through the Grasshopper to have a certain optimization to bring this number of repetition to the adequate level. So it's actually in 3D. So this granite slabs, they're really big granite slabs. They get up and lower and different pattern. And we introduced, we designed, invented our own scripts to help with paneling. And this is finally we have this table of typical panels, and this is how we help to reduce the budget. Thank you very much for your attention. If you have any questions, I'm happy to answer.
Thank you very much for a very interesting presentation of an outstanding project. And yes, we have one question here, and I will read it for you. The question is from Arthur Tomchak, and it reads, I admire many of the projects shown here from the structural and architectural point of view. However, isn't a sustainable skyscraper an oxymoron? For technical reasons, both embodied and operational carbon footprint per area of such structures is significantly higher. Lead platinum doesn't change this. Mr. Nikandrov, as a person involved with both the Tall and Green Buildings Journal, could you please share your opinion on this topic?
Yes, it's a sort of eternal discussion on the sustainability of skyscrapers, but it's not about even architecture; it's about town planning. So if you get to the great level of town planning, skyscrapers are more sustainable because they save the most important asset on Earth, which is land. So the land area. If you increase the concentration in town planning in the city, in megapolises, you can see that the actual rise of the towers is a result of high cost of land and the use of land and infrastructure. So you actually save land, which is a major sustainable element in the whole thing. If you imagine Hong Kong or Dubai spread as a village, instead of skyscrapers, you replace them by 2-story blocks or 5-story blocks, you will get the huge mega city like Mexico or Rio, or you get a huge favela, and favela is not sustainable, I would tell you, because it spreads all over the place and consumes. So it's consumption of land. Important territories, and again, of course, it's more sustainable to concentrate users in one, because you have in multifunction buildings, you reduce the number of you reduce the need for transportation between one area to another area, which is a major problem of megacities. This is the traffic between between residential area to the industrial area or downtown or shopping malls. And all this traffic in between, and you get a lot of pollution, a lot of air pollution and CO production as a result. But when you concentrate these users in the vertical city, what we call vertical city, the towers, downtown, you have everything inside. You have then you have a pedestrian movement between one tower to another. Again, you can use sky bridges between the towers. This is basically a sustainable thing in all this is a third direction of development. When city gets developed in XY directions, like horizontally, right? Then you kill the nature, but you have Z axis and you rise vertically, and you concentrate vertically. This is you save your land, you save area.
Thank you very much, both for the wonderful presentation and for your opinion on this question. This is also very interesting. So I don't see any more questions here. People, thank you for your interesting presentation. Now, we have